Good morning and good afternoon, everyone. My name is Kenta Horikawa, and I'm honored to have this opportunity. Let me introduce our project, 10 Steps from Event Focus Stack. As you know, depth estimation is a fundamental problem in computer vision, with applications ranging from robotics and autonomous vehicles to augmented reality. Conventional image-based methods rely on analyzing motion, disparities, or defocus. These methods have some advantages like less expensive and more space-saving than other input modalities. However, these methods often struggle under extreme conditions such as rapid motion or low-light environments. To address these issues of image-based methods, event-based camera has attracted attention. Event-based cameras output events which record brightness changes asynchronously. Due to these characteristics, event-based cameras offer advantages such as high temporal resolution, high dynamic range, and no motion blur. There is a similar project of image-based method called focus on defocus. This method estimates the dense depth map by image focus stack to address the domain gap between synthetic and real data, but it cannot perform well on the extreme light conditions. There are some existing methods of event-based depth estimation. These methods are robust to extreme conditions like rapid motion and low-light environments. However, existing methods assume changes in camera position or angle or the movement of objects within the scene. As a result, they cannot be applied to static scenes where no events are generated. To address these challenges, we propose a novel approach. The proposed method aims to estimate the dense depths utilizing the events from focal blur and focal point. The framework is as shown below. The input is only the events from focal sweep, and the output is the inverse depth image. When we collect the events, the camera position and angle are static, so the most part of the events from focal sweep are the events triggered by out of focus and in focus. The model is trained on synthetic data and then fine-tuned with real capture data to address domain gap between synthetic and real. Event focus stack is a voxelized 3D representation of the events from focal sweep. This structure allows for effective depth inference using convolutional neural networks. To capture both spatial and temporal information, the event polarities are weighted with timestamps. We conducted experiments about bin size of the stack and determined bin size as 5. Our method employs a unit-like architecture to map the event focus stack to a dense depth map. This follows the event-based video reconstruction method. We optimize the network using a combination of synthetic and real capture datasets to ensure robust performance. We use MSE loss that computes each pixel errors between ground truth depth image and predicted depth images for loss function. We also created our own datasets to support the proposed method. The synthetic dataset was generated by first creating image focus stacks using Blender. Then virtual events were generated from these stacks using the event simulators. At the same time, ground truth depth images were collected as difference data. Using this process, we collected data for 1,000 scenes. The real capture dataset was constructed using a Davis 346 camera equipped with a computer-controlled lens to capture event data and intensity images. To correct for the lens breathing phenomenon, which caused field of view changes during focus sweeps, homography matrices were applied. Using this process, we created data for 60 scenes, covering both office light and low light conditions. To evaluate the performance of our proposed method, we use two metrics, mean absolute error (MAE) and root mean squared error (RMSE). MAE calculates the average absolute difference between the estimated and the ground truth depth values. RMSE computes the square root of the average squared difference between the estimated and the ground truth values. Both of MAE and RMSE are the metrics that smaller is better. Additionally, RMSE is sensitive to outliers, making it useful for determining their presence. The table below summarizes the results of our evaluation. Compared to the baseline method, our proposed approach demonstrates superior performance for both MAE and RMSE metrics. Specifically, our method could reduce the error by up to 50%. Also, here is the qualitative result of synthetic data. In the generated depth image, bright orange indicates objects closer to the camera, while deep purple represents objects farther away. In the error images, blue areas indicate small errors, whereas red areas indicate large errors. This result shows that ours are less errors and clearer edges. This is thought to be because the high temporal resolution of the event-based camera allows the focal sweep to be observed in detail. Here is a qualitative result of real capture data. The horizontal rows show the same thing under varying illumination conditions. The results obtained finally are highlighted in red. The generated depth shows fewer inconsistencies and performs well even in low light conditions. Compared to the results without fine-tuning, the effect of fine-tuning is evident. Additionally, for the image-based method, the depth estimation is inverted even under bright conditions, and it fails completely in low-light environments. In contrast, our method achieved better results in both of the lighting conditions. By comparing the inputs and the outputs, the difference between image-based and event-based approaches becomes clear. For the intensity images in low-light conditions, we cannot find the details of the objects. By contrast, for the events in low-light conditions, we can observe the pattern of focal sweeping. This difference is particularly significant, and it is reflected in the generated results. From the comparison in with fine-tuning and without fine-tuning in the result of real capture data, it can be said that there is severe domain gap between synthetic and real captured events. While the real event shows positive and negative patterns with focal sweeping, virtual events show only positive events and almost no negative events. This topic indicates that virtual events cannot correctly follow the focal sweeping. Also, in the image-based method, the focus blur is often said to be domain invariant, but in the event-based method like ours, the focus blur may cause severe domain gap. Finally, the overview is here. We propose novel framework of dense depth estimation from event focal stack. To tackle this task, we created our own synthetic and real capture dataset. Our method shows better accuracy on both synthetic and real capture data and more robust to low light conditions than image-based similar method. But by investigating the domain gap between synthetic and real events, we found that it is very difficult to make the synthetic events approach the real events, and we should continue to work on improving our synthetic dataset. This is the end of our presentation. We will be waiting on March 1st at poster session 2, and our paper ID is 2203. Thank you very much for your attention.